Right, some of you are really super quick. Okay, thanks for coming. And what I thought I'd start off with, there were some questions as well as some misconceptions when I was marking the 3041A for some students. So I thought I'd just deal with those first, and then we'll go on to the intermolecular forces that are covered in CH3042. So this first, what you can see on the screen there is it's a hypothetical ion. We obviously don't get an element that has 3 protons with 3 electrons all in the same energy level. I've just made it like this simply because I didn't want to change shell sizes, and I didn't want to have the problem of full energy levels or not. So we've got this hypothetical element, call it X, right? What is the nuclear charge on this element? If it has 3 protons, plus 3, correct. And because I don't have any inner energy levels, there's no shielding, so that is the charge in the nucleus which is going to be attracting my electrons. So what I've got up here is, because I didn't really deal with the repulsion side, which is important to think of when you're working with the size of ions. The attraction is between this nucleus, the nuclear charge, or effective nuclear charge if you've got shielding, and each individual electron. So that Q1 will be plus 3 over here, and the Q2 will be the minus 1 over there. Okay, and then of course the distance is how far those electrons are from the nucleus. But we've also got a repulsion, and it's important to think of that when you deal with ions. When you're just dealing with atoms, everything is in balance, the whole size depends on the repulsion and the attraction, but ions, we're changing that charge. So we've got our attractive force there, okay, our F attraction, and we also have the repulsion between this electron and that one, and that one, and so on. Okay, so let's look now what happens if we lose an electron. So we're forming a cation. Now, the nuclear charge is still plus 3. Okay, so we've still got plus 3 there. We've still got minus 1 there because we're looking at the attraction of the nucleus on the electron. So that hasn't changed in terms of the attraction as is. We'll see the change just now, but what happens now is we're going to have repulsion between those electrons. And what do you think is going to happen to those electrons? So see, some of you are typing. They move away more from each other. They want to be the maximum distance. As I say, we're not talking about now spinning one direction or the other. We're just dealing with a very simple hypothetical case. So it tries to move as far away as possible, but it still has the same repulsion between those 2 negative charges. So what happens is the atom, well, the ion now, shrinks in. Okay, because this electron will still repel the same amount, so they can now get closer because there are fewer of them. So it's here the same quantity. I think you meant the quantity of charge, Joe. Yes, because you got one electron just repelling the same charge on the other electron, and so because they've got the same repulsion, it can go closer to have the same level of repulsion. So here they were a certain distance apart. So here now the whole atom can shrink, or whole ion can shrink, sorry, to be that same distance apart as they were over there. So if you answer a question like this and you say the cation is smaller than the atom, it's not because of the charge on the nucleus is shared over fewer electrons. That's a totally wrong misconception. I've seen YouTube videos out there It was actually mentioned at the conference last year, the chemistry conference, about common misconceptions. We don't have the sharing of charge. It's always between one charge system and the other. So there's no sharing, but it's because we've got fewer electrons, there's less of that electron repulsion. So if I go the other way, okay, so I'm trying to show one last thing here. I hope you can see this is fatter and wider because this attractive force has now actually got bigger. Why is this attractive force now bigger in the cation than in the atom? So no, Caleb and Joe are typing. I don't know if they were starting to type beforehand. Yep, so we're going to go into the anion. I'd forgotten this is about the cation. Yep, so Caleb, the less proton electrons to proton ratio is fine as an indication of what is going to happen, but it's not an explanation, because that's where the misconception of sharing of electrons or sharing of nuclear charge and so on comes in. So it's a good way of seeing what happens. So it's a measure, if you like, but it's not an explanation. Okay, so but can you see that this attractive force, this has actually increased from the atom to the ion? And why has it increased? I've just told you that the one charge is still +3 and the charge on the electron is still -1. What has changed? The distance, this bit over here. Because there's less repulsion, the electrons come closer to the nucleus, which allows this attractive force to get stronger and pull it in even a bit more closely. So as I say, the amount it pulls it in is also dependent on the repulsion. So it can't pull it in forever and have them right in the nucleus. The repulsion between the electrons is still going to keep them out there. Okay, so it's this balance between there always has to be a balance between the attractive force and the repulsive force. So if we have now the other side, so there's my atom again, and I'm now adding an electron. The electrons, we said, will repel each other. So it's X minus. So the Z is still +3 because we haven't changed this. And so I'm trying to show them expanding apart. Okay, because you probably can't see it, but I try to keep all these arrows the same length. They still want the same repulsion between them. That's bad wording. They're not humans. They still have the same repulsion between them, so that's why they've moved further apart. And of course, then that has actually decreased the attractive force as well, because the electrons are now further away. So you can still talk about that pens, the number of protons, the electrons and energy level, the nuclear charge, the distance. You still talk about those. But when you talk about ions, you have to also talk about the repulsion. So this category of repulsion only comes in when you're discussing the sizes of ions. So very quickly, formation of a cation. Here's one that's not hypothetical for magnesium. Your effective nuclear charge is your total number of protons, subtract all the inner electrons. So these valence electrons here sort of feel a charge of 2, okay? And there's a certain distance between them. If I now I've removed these valence electrons, so you can see they're gone. So my valence shell is now much closer. So you must mention that you've decreased by an energy level. So your distance has decreased because of that. And as I say, it can now pull in even more because of that stronger attraction with less shielding. Can you see ZF has changed from 2 to 10? So it's a much stronger force of attraction. Okay, and it'll pull it in until the repulsion between the electrons stops it from pulling in anymore. And finally, the anions. Here's an example sulfur. So 16 protons, and we've got 10 in the electrons. So those valence electrons each have a nuclear charge of +6 attracting them. And if I now make the anion, so I've added 2 extra electrons. You can see there's one more over there and one more over there. And we still have the same +6 charge, and we now have actually more repulsion. I couldn't really show it well in this diagram because I lumped these two together, but there is that more repulsion. So it's spread out further, resulting in a smaller charge. Oh, sorry, I meant to go back. Right. So it was supposed to show it going bigger, and I think you can see that that is bigger. Any questions on formation of ions and explaining that? So I hope that's clarified things. And has anybody completed CH3041A? So none of you? No? Okay. Oh, you have? Okay. So just there is that one question asking about the formation of ions. Right. The other question I had was a student asked, I said, use the periodic trends to give you an indication of the changes in electronegativity. So she wanted to know, is one expected to know whether, say, boron over here is more or less electronegative than, say, an element down here? So the answer is no. You expect it to know big trends. So if I show something like this, can you see how if I take the electronegativity of lithium and then across, there's a change from 1 to 4, so it's an extra 3. But if I go down a group, it's only a 0.1 change. So because there's no change in shielding, there's a much bigger effect going across because you're adding protons, but there's no change in shielding. If you go down, you're adding protons, but you've also increased that shielding a lot. I think you saw that with that magnesium going from a nuclear charge of 12 to 2. So there's not much change there, but across there is still a big change. So you wouldn't be expected to know any of these values off by heart. You wouldn't expect to know that, say, carbon is more or less electronegative than phosphorus. Okay. You will get to know them over time, but don't worry about it. You wouldn't be expected. What you are expected to know, and this will come up in today's lesson, that nitrogen, oxygen, and fluorine are the most electronegative elements. So if you've got fluorine with anything else, fluorine is always going to be the more electronegative. If you've got oxygen with anything else apart from fluorine, it's going to be the more electronegative one. And the same thing for nitrogen. Now you can say nitrogen is 3 and chlorine is 3, so why am I not talking about chlorine? It's not just really the electronegativity, it's also to do with the size. Nitrogen is a lot smaller, so any bonding electrons it has, they're much closer to it, so nitrogen has a bigger effect than the chlorine. Chlorine is much bigger, so although it's got a similar attraction, they're further away, so it won't be felt as strongly. So these form hydrogen bonding, but chlorine doesn't. Germany, I've looked at some German videos on YouTube, and they include it as hydrogen bonding, but I have otherwise not seen anywhere else. Any questions on periodic trends? No. Okay, let's get going then on the intermolecular forces. This is another one where it distinguishes between achieved merit or excellence, depending on your level of detail. If there's time, we'll discuss entropy, so I'll put it down here. But I want to focus on the intermolecular forces. Okay, there are three types of intermolecular forces. Now, has anybody here started CH3042? Nope. Okay. So this is, as I say, the main focus. When you've worked out the Lewis structure, you can then work out the shape of the molecule, and then you can then work out whether the molecule is polar or non-polar. Now, if you've got any molecule actually, any molecule that has electrons will always have temporary dipole forces of attraction. These are very instantaneous type of attractions caused by electrons moving around the nucleus, or so for a very short period of time, one side of the molecule can be more electron rich, and then split second later those electrons have moved on, so now it's on the electron poor side. Okay, it's found in all molecules, well, all molecules that have electrons, and they do. Okay, and there are three things that influence the size. So they're normally the weakest, but notice I said normally, because sometimes they can be stronger than anything else, depending on these three factors. The mass of a molecule. If a molecule contains very heavy elements like bromine and so on, the forces of attraction are much stronger. I think you can see that HCl is a gas. HI is not, because of the iodine as being so much bigger. There are stronger forces of attraction between them. So what I'm trying to show here is, here's my non-polar molecule. It could be polar as well, but just for argument's sake, there's attraction between them. If I double the mass, I'm going to make a much stronger attraction between them. So it'll be harder to separate these two molecules. I'm going to have to put in more energy to take them apart, or to move the, take the molecules apart sounds as though I'm breaking up the molecules. So to move the molecules away from each other, it requires more energy for this one than that one. Okay, the number of electrons. So anything with more electrons means, remember, it's caused by electrons moving around. So if I've got lots of electrons, they can all go on one side and become very negative on this side and very positive on the other side, and a split second later it can flip around. But the more electrons you've got, the more you can make the charge move around. So that affects the strength, because the bigger the charge difference, the more it'll act like a stronger magnet, if you like, and attract things. And then the shape of the molecule. If you've got a sort of a very round shape or awkward shape that can't get close to another molecule, you can't form very many attractions. But if you've got a nice sort of flat, long shape that can go close to another flat, long shape, lots of attractions can form. So you've got to break lots of attractions, so you're going to need more energy to do that. Okay, so there's an example of something that's round, so it can't form very many attractions. But if I have the same mass molecule but a longer version, then I can form a lot more attractions between them. So that's sort of in brief. A diamond is something slightly different, but it's one of the reasons. That is not because of intermolecular forces. It's interatomic ones, which is a covalent bond, and that is very fixed. Those bonds, yes, the lattice, correct. It's that lattice is very directional, those bonds, so it's very rigid, and those atoms can't move, so it becomes very hard. There's no sort of give between them because it's a tetrahedral structure and it's very fixed in position. And then, as I say, it's usually weak. It's normally the weakest, but remember, the bigger the molecule, the more the mass, the more the electrons, the stronger those forces of attraction. So methane, CH4, is nonpolar, it's a gas, but tetrachloromethane, although it's non-polar, it will be a liquid because of those heavy chlorine atoms. Okay, I'm going to show this now because this is quite a good thing to see. This is also, or it should be on your site. I'm going to try and make it bigger. Yep. What we're trying to show here is a molecule that's non-polar. Don't worry about the London dispersion attractions. That's a term used in the States and in Britain. It's the temporary dipole forces of attraction or instantaneous dipole forces of attraction. Same thing. If you call them London dispersion forces in the exam, that's fine. You wouldn't be marked down. But can you notice, can you see that change in color? The blue being more positive, the red being more negative. Can you see that color changing constantly in this section over here? Yep. So those are those electrons moving around the molecule. And because those electrons are constantly moving and so on, we're getting constant changes in the electron distribution. And so for all these brief instances, as you can see with those flashing green lines, those are those dipole forces of attraction. Yeah, white would be neutral. Okay, so that's when things are evenly balanced across there. So those green things are the temporary dipole forces of attraction. So I find this quite a good image to see, that it's there and any molecule has it. So here's a polar molecule, right? So you can see it's polar. It's got always one side blue and the other side red. Here, can you see it changes between blue and red? Okay, each end, because there's, on average, there's an equal distribution. Joe, no, the magnetic molecule, magnetism is something slightly different. But we often use electron charges because they influence, or because they act in a similar way to magnets, that we often use that example. But this is a slightly positive end and that's a slightly negative end, but this is in terms of charge, not a magnet positive, like a magnet North Pole and a magnet South Pole. Okay. These will be influenced by a magnet because any moving charge is affected by a magnetic field, and the other way around, the magnetic field is affected by moving charge. Right, so you can see this one is polar because it's got a positive end and a negative end. Do you use dipoles? Do you? Okay, because dipoles are separation in charge, an electric charge. Is that? Yeah. Okay. Yep. That's the way the electrons tend to line up in their orbitals. And yeah. Okay. Fine. I'll look that up just to make, because the ferromagnetic ones, if you've got all the electrons, you know, remember I said one spins in the clockwise and the other one spins anti-clockwise. So if all the molecules are paired like that, if all the electrons are paired like that and they spin in opposite directions, that element is not magnetic. If you have where a lot of them say all spin in the clockwise direction and they're not paired, then we get what we call the diamagnetic is when it's not, well, that's when it can be magnetic. The ferromagnetic is a slightly different case again, where that has been made more pronounced, that effect. So that's why not every element tends to be magnetic. Oxygen, for instance, you can turn oxygen into a magnet, but it's not as strong, say, as iron, because it doesn't have that extra effect. Yep, I haven't explained it very well at all. Okay, right. So can you see here, these green lines don't move compared to that. These are all flickering around all the time because it's instantaneous. These are permanent forces of attraction. This end is always positive, sorry, negative because it's red, and this end is always positive. So there's always going to be attraction between them if it's lined up in a lattice, for instance, or if those two come close together, they'll immediately attract each other. So are you clear the difference between these quick attractions being temporary and these permanent attractions? They're two different concepts. These you only find in polar molecules. You do not find them in non-polar molecules. In polar molecules, however, can you see though, this red isn't always the same red, and the blue isn't always the same blue. Sometimes the red is a brighter red, and then it's more white, and the blue is sometimes a brighter blue, and then more white. And that's because in any molecule you've got those electrons moving. So even though you've got that uneven distribution of charge, they still can move around a bit. And that means you're also going to get temporary forces just like that appearing in here as well. So you'll, just like you get those quick ones up there, you'll have them down here. It's just in the polar molecules you'll have those plus these permanent ones. Any questions on that? No. Okay. So recap this. The strength of these attractions are affected by the mass of the molecule, the number of electrons, and the shape of the molecule. So you can actually get very strong instantaneous forces of attraction. The polar molecules have got both those temporary forces of attraction as well as the permanent force. And what do you think affects the size of the permanent force of attraction? What will make this bigger or smaller, these green attractions? So Caleb is typing. Not the mass of the molecule. The mass of the molecule is only affects the temporary dipole force of attraction. Caleb, yep, you're on the right track. It's the more polar the molecule. So the bigger the molecular dipole means the more negative one end is and more positive the other end of the molecule is. So the bigger that dipole, the bigger that separation of charge, the stronger that permanent force of attraction. Yep. So if you have a very electronegative element like fluorine, so like HF, has got a very big separation of charge. April, why the temporary dipoles in polar molecules? Because those electrons are still moving. In a polar molecule, we don't have just a whole lot of electrons sitting on one side and hardly any on the other side staying there without moving. Electrons move constantly all the time around the nuclei. So because the electrons are moving, you're not going to have always the same negative charge on this side and the same positive charge on that side. So as you can see, there's a fluctuation in the charge. So you're going to have the permanent ones that are stuck there by the dipoles, the permanent dipoles, but then you're also going to have these same temporary ones. Yes, even though the main charge doesn't change much. Correct. So again, the bigger the molecule, so if you've got a very big polar molecule, you're going to have quite big temporary dipole forces of attraction between them. And that may be even the most important force of attraction. If you've got a polar molecule that's not got a particularly big molecular dipole, so the permanent dipole force of attraction isn't very much, but it's big and heavy, then you're going to have a lot of those temporary forces of attraction. Okay, so as I say, this is, I think, is a very good visual image. You can sort of freeze it, so you can sort of see that blue is not quite the same. You know, they differ a bit. Or you could take the average, so non-polar, you can see is white, because on average the electrons are evenly distributed. Here, so the white's only in the middle, because you've got the positive and negative end. Right. Um, just getting back to this one now. So that's a temporary, and we've actually already talked now about the permanent force of attraction. This you only get in polar molecules. The previous one, temporary, you get in everything, and the permanent you only get in polar molecules. Now notice this is just part of the van der Waals forces of attraction. At level 2, we basically just talked about the van der Waals forces of attraction. Level 3, you need to break it down into the temporary and the permanent. If you just said van der Waals forces of attraction are weak and blah 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 like you did in level 2, you're not even going to get achieved, because that's level 2 thinking. You're now going deeper into level 3. Okay, so if I go back to this last viewed, these are the different names. Instantaneous dipole, forces of attraction, same thing as temporary dipole. So pick one and keep to it between those two. London forces, dispersion forces can also be used for this type, and it's part of the van der Waals. Van der Waals forces cover both the temporary and the permanent dipole force of attraction. Okay, so it's found in polar molecules, and it's influenced by the size of the molecular dipole. Sorry. So here I'm trying to show not much separation in charge, small molecular dipole. Here, a big separation in charge, so bigger molecular dipole, so the force of attraction between them is much stronger. But of course, any polar molecule also has the temporary dipole forces of attraction. So what I'm trying to show here is how at the boiling points, which is a measure of, or it's a type of measure of the strength of the intermolecular forces, because a high boiling point has what? Strong or weak intermolecular forces of attraction. Strong, correct. Okay, because you must clearly state that you need a lot of energy to separate the molecules from each other, because remember, in a gaseous phase, because boiling means we're going from liquid to gas, so in a gaseous phase all the molecules have separated from each other, so you've broken all the intermolecular forces between them. Liquid, you've only broken some of them. Gas, you've had to break all of them. So it's a good measure of how strong those intermolecular forces are, because the more energy you've got to add to separate, the stronger those intermolecular forces. So here's CCl4, and you hope you're madly doing your Lewis structure and then your shape of your molecule, which is tetrahedral, and you'll see that it's totally symmetrical. So is carbon tetrachloride polar or non-polar? Non-polar, correct. But have a look at its boiling point, 76 degrees. It's a liquid at room temperature. Here's CHCl3, or CH3Cl. This is a polar molecule, not very strongly polar, it's only weakly polar, okay, but it's a gas at room temperature. So this one has both the temporary and the permanent dipole forces of attraction. This one has only got the temporary, but why is this one 76 degrees and this one minus 24? The clue is in the orange. No, this is grams per mole. It's a molar mass. Concentration is mole per liter. Um, Small intermolecular charges. I think you're trying to string a few ideas together there. Are you trying to talk about a molecular dipole? There's no molecular dipole over here. It's a non-polar molecule. This one is a polar molecule. Not, as I say, very polar, but it's still polar. But remember the things. Okay, what's the question? Why is this non-polar molecule a liquid? It's got a high boiling point, whereas this polar molecule that has two types of intermolecular forces holding it together is a gas. So it's got a lower boiling point. And yes, April, it's the size and the mass of the molecule and the number of electrons. They've got the same sort of shape. They're both tetrahedral. Okay, yep. Terminology in this 3.4 standard can be very tricky because you've got a lot of very similar sounding words. So always read over your answer to check that you've used the terms correctly. I think in the last lesson I was using electronegativity incorrectly when I said this end is more electronegative. That's wrong. Okay, this end is more negative. Electronegative is a property of an atom, not a molecule. You can never have an electronegative molecule. Okay, right, so this is a much heavier molecule, so those temporary dipole forces of attraction are much stronger in here, giving this a much higher boiling point. Here, although this is polar, it's only weakly polar, so you've only got weaker permanent dipole force of attraction, and it's not very heavy, so you've got even weaker temporary forces of attraction. Yep. So Joe, the bigger the molecule, the bigger the temporary dipole force of attraction. Not just any one; it's always the temporary one. Okay. The same thing here with CH4, non-polar, but it's very light. It's only 16. Okay. Take it to CHF. It's although it's still negative, it's still a gas. Can you see it's quite a bit higher than minus 161? And it's not that much difference. It's double the mass. But the reason here is partly because of the mass. The bigger the mass, the stronger the temporary dipole force of attraction. But also here there'll be quite a big dipole, a molecular dipole. So it'll be this stronger separation or bigger separation of charge. So it'll be a stronger force of attraction. And you know that because F is very electronegative, so it's going to be pulling electrons to itself. Okay. Now, Joe, you had there because. Have I answered your question? See. Oh, okay, right. And then the same thing here. We've got here a sort of slightly longer molecule of propane, which is pretty much non-polar. Anything with a dipole of less than 0.5 is considered non-polar, actually. Similar mass, 44 to 48, but you'll see there is this difference. This one has a higher boiling point because of the fluorine. The fluorine just makes it slightly more polar, and so it'll have that permanent dipole force of attraction. Okay, so those are the two main ones, and make sure you always discuss both of them for polar molecules and the temporary one for non-polar molecules. Then there's a certain category of molecules that have hydrogen bonding. This is, if you like, an extreme end of the permanent dipole force of attraction, but we give it a separate name because you only find it when you have a hydrogen atom bonded, you only find it in molecules that have a hydrogen atom bonded to a nitrogen, oxygen, or fluorine. Now, this HN bond, or HO bond, or HF bond, is not the hydrogen bond. So if you think you've got a molecule, and within that molecule is the NH. Okay? So be very careful of your wording. So here's a water, OH, OH. Right, so water can have hydrogen bonding because it's got a hydrogen attached to an oxygen. The hydrogen bond is not this one over here, which is covalent. It's this pink attraction between the water molecules. So when you're trying to explain this, again read over your paragraph, because so often I can see you know what you're talking about, but it comes across as though you're describing this bond over here instead of that one. So my suggestion is always draw a picture. So if you're trying to frantically write a whole lot of things, it's just so much easier. Sketch out your two water molecules or your HF molecules or whatever you've been given, and then draw a line like this between them and label this hydrogen bond. Then the teacher knows exactly, yes, in your answer. So sketch it out so it's part of your answer, and then label this hydrogen bond. Because sometimes a teacher is going to read this and think, now, did the student mean this hydrogen attached to this oxygen in the same molecule, or did they mean the hydrogen being attracted to an oxygen of another molecule? So that is the problem, is sometimes the wording is not very clear. So always think of, when you read over your answer, just ask yourself, if somebody else was reading this, will they know I'm talking about the attraction between a hydrogen in one molecule with an oxygen of another molecule? Okay, and as I said, the quickest way is just to also draw a sketch. Okay, and as I say, this is a very strong force of attraction because oxygen is extremely electronegative, small molecule, extremely electronegative. Hydrogen, it's only got 2 electrons. Yes, it's in your DNA and so on as well. So it strips pretty much the hydrogen of its electrons. So you've got like a proton sitting there, totally positive. So it's very strongly attracted to the lone pairs of electrons around an oxygen. And it can do this for nitrogen, and it can do it with fluorine. Fluorine is the smallest molecule of the three, and this, has the biggest nuclear charge because it's got the most number of protons, so that while fluorine has the strongest, can form the strongest bonds, hydrogen bonds between them. Okay, and as you said there, it's in the DNA, it's what holds the helix together. So guanine or the CTAG or whatever, that holds it in that way. Okay, now regarding solubility, because this one is the strongest of the 3 different types, it's going to need the most amount of energy to break. Okay, if it needs the most amount of energy to break, when something has to dissolve, you have to break those bonds, those hydrogen bonds, which means when something dissolves, the attractive forces between the solute and the water must be similar in energy to the hydrogen bonds within the water molecule, because the energy given off by the attractions must be enough to break the hydrogen bonds, so that we've got a sort of similar level of energy. So substances that can form hydrogen bonds, like ethanol, will dissolve in water. Okay, but other substances that don't have hydrogen bonds could still dissolve in water. So this is an example of formaldehyde. You'd use it in biology as a preservative. Okay, the hydrogen of the water can form attractions with the lone pair on this oxygen. So although formaldehyde does not form hydrogen bonds in itself, so it's a gas, okay, and not a liquid like water, but when you bubble this gas through water, it will dissolve because the water can form hydrogen bonds with it. Does that make sense? Okay, right. So let's have a quick quiz. BRF3. Now you've got to ask yourself, remember how I said you've got to go through this, the Lewis structure, the shape, then you look at the polarity, and then by knowing whether it's non-polar or polar, you can work out the different types of intermolecular forces. So what do you think that BF3 will be? Okay, you got the right. It actually is a polar molecule. Good, April. The reason being, bromine has got 7 electrons, fluorine has got 7 electrons each. So we're saying 7 times 4 is 28, which means that bromine there is going to have an extra pair of electrons. So the shape is not going to be a symmetrical shape. Do you want me to sketch that out? Or do you think you'll be okay? Okay. So let's go, as I say, you have to draw the Lewis structures to work it out. So this one is non-polar, so it'll only be temporary. This one is non-polar, so only temporary forces of attraction. Ozone is a bit of a tricky one because you'd think, oh, oxygen, there's no difference in electronegativity, so it should be non-polar. But remember, we looked at it at that last lesson. Although the bonds are non-polar. Okay, Joe, right. You're doing very well to keep your attention here. So although there's no difference in electronegativity, because of the shape of ozone, you're going to have a different distribution of charge. So there is a separation of charge, so ozone is actually polar. The middle oxygen hasn't got as many electrons around it as the ends. Okay, methanol, I hope you see that OH in there, and hopefully that'll trigger the fact that there's hydrogen bonding. You won't have hydrogen bonding in any of these because in none of these you don't have hydrogen attached to a fluorine or to an oxygen or to a nitrogen. Okay. Now, the way this comes up in the exams is they ask for the properties about boiling point or solubility. So first is what is boiling point, and I've just given it here because I just see we've got 10 minutes left. It's the temperature at which a substance changes from a liquid state to a gaseous state. A lot of students will just simply say it's when it changes from liquid to gas. Can you see the difference between when it changes from liquid to gas to the temperature at which a substance changes from liquid to gas? So be specific. Okay, you wouldn't have got anything for that other one because we go, well, when, tell me what I'm measuring. Okay, so when you boil, you pretty much, I said here most of, but it's pretty much all of them because you have to separate the molecules. Be careful of wording. So when you say most of them intermolecular, to break the molecules, I've seen. Now, break the molecules sounds as though you're actually splitting up the molecules into its atoms. So be careful of wording. Separate the molecules means you moving the molecules apart, but you're still keeping the molecules intact. If you say break the molecules, it sounds as though you're bashing them up. Okay, so here's an example. Here's your non-polar methane, your non-polar CF4, but here's your polar CHF, and you have to explain these. And so you would talk about intermolecular forces for all of them, temporary in all three cases, permanent only in this case. You would then also talk about mass having an effect. So although this is non-polar and that's non-polar, which one do you think has the bigger mass? CH4 or CF4? The latter, the CF4, correct. And because it's got a bigger mass, That's why CH4 is minus 164 and CF4 is so much higher. I mean, I know it's still negative, but it's still a lot higher than this one. Okay, so identify the type of intermolecular forces, think of the factors affecting them. So don't just say, oh, CF4 has got a bigger mass, so it'll have a higher boiling point. Say CF4 has got a bigger mass than the methane, so the temporary dipole forces of attraction will be stronger. So we'll need more energy to break those forces and so on. So link the bigger mass to the temporary dipole force of attraction and not just to intermolecular forces in general. So be specific. Okay, and then here you talk about the polarity, so you'd have your permanent dipole force of attraction there, and there'll be a big dipole there. Okay, so here I've given like a model answer. Can you see I'm being very specific? Okay, I'm spelling out each of the different types, and I'm talking about the factors, heavier, more electrons, and I'm saying which type it's affecting, the temporary dipole force of attraction. They are stronger, so more energy to break to separate the molecules. Okay, and then you do the same thing with this one, but now talking about the permanent dipole force of attraction. Okay, and notice I haven't ignored the temporary dipole force of attraction in CF4. I haven't just said, oh, it's got the permanent dipole. I do talk about the temporary dipole. I look at its mass and I see, is it stronger or weaker? So it'll be less than that, but more than that. So I include that in my discussion. Okay, how do you know which dipole is affected? This is, as I say, you need to know if there's a polar molecule. And the way you know whether it's a polar molecule or not is by drawing the Lewis structures, looking at the shape, and then working it out. So you are expected to be able to work out if the molecules are polar or not, and if they are polar, then you're going to have the permanent dipole force of attraction. Okay, and you could, if you wanted to state that there's no hydrogen bonding present because you don't have a hydrogen bonded to an electronegative F or O or N, because here the electronegative F is bonded to the C, and the same over here. It's not bonded to the H. Right, so here's last year's exam. Okay, you get given 2 isomers. If you did last year organic chemistry, you'll know these are isomers, same molecular formula, but different connectivity, the way they're connected together. So this is this long, sort of flattish molecule. This one is quite a round molecule. Okay, so first of all, list all the forces of attraction between them. Does it have only one type, 2 types, or 3 types of forces of attraction? 3. Correct. Because being a molecule, it'll have the temporary dipole force of attraction. It's polar because of this end. I know this end is pretty much non-polar, but this end is polar. So it'll have the permanent dipole force of attraction, and it's got an OH. The hydrogen is bonded to an electronegative oxygen, so it'll have hydrogen bonding. So there you go, you list them. Then you have to explain why this one has a higher boiling point than that one. So you basically say, well, look, they've got the same hydrogen bonding because they've got identical isomers. Okay, I mean they both got the same molecular formula. So they both have hydrogen bonding. The dipole moments will be similar, so the permanent dipole force of attraction will also be similar. Okay, you don't have to go and know the exact details of it. You just say, well, you've got a non-polar end and a polar end and a non-polar end and a polar end, so it's a similar separation of charge. So the what you now need to focus on is the factors affecting the temporary dipole forces of attraction. So mention that you can recognize the hydrogen bonding, you can recognize a permanent dipole, but then start focusing on the three factors that affect the temporary dipole. So the long, thin molecule, so that you can form more attractive forces across it than a round one. But show also same mass, so that won't affect the temporary dipole force of attraction, and same number of electrons. So can you see how for excellence you've got to hone in on every little detail and spell it out. Don't assume that the teacher will know. We're not allowed to read your mind. Okay, so list everything. Okay, here's one from 2014. So they give you ammonia, fluorine, hydrogen chloride. So all of them are going to have the temporary dipole force of attraction. Which one of these three is going to have the hydrogen bonding? Okay, you got the non or F. April, I can't decipher that. So, none. Okay. Remember, hydrogen bonding is when you've got you find it in molecules where a hydrogen is bonded directly to a nitrogen or a fluorine or oxygen. And here you have got a hydrogen bonded to a nitrogen. You don't have it here. And here, although you've got a hydrogen, it's to a chlorine. Now, I know chlorine and nitrogen have got the same electronegativity, but chlorine's a lot bigger, so it won't do hydrogen bonding. So this one is hydrogen bonding, and that's why it's got the highest boiling point. Okay, so April, does this make sense now that I've pointed that out? So to see some of you are typing there. Yeah, no, it can be to a nitrogen or to a fluorine. Okay. So you look at the molecule and see, is there a hydrogen that's bonded to an oxygen or to a nitrogen or to a fluorine? So you've got to have that bond. And if it does have that bond, then that molecule can form hydrogen bonds to other molecules. Okay, so there's basically the answers. And you'd remember, you'd look at the temporary dipole force of attraction, you'd compare M. There's not much you can compare in terms of shape. These are two linear molecules. That one's, they're all small molecules. And again, show everything you know about the temporary, the permanent, and the hydrogen bonds. So what the factors affect them and so on. And have all those things. So the conditions for hydrogen bonding, so it'll only occur in ammonia. And then, of course, the whole point of boiling point is the energy needed to break those intermolecular forces to separate the molecules in order to turn it into a gas. So show that this energy, but to separate the molecules. Okay, right. Okay, we're pretty much now 4 o'clock. So here you can see this is a similar sort of thing. Now can you see the hydrazine? So you can be given molecules you wouldn't normally come across, like hydrazine, okay? But you would still be expected to be able to draw the Lewis structure, see that N and H, this will have hydrogen bonding, okay? You won't have hydrogen bonding here, and you won't have hydrogen bonding there. You should be able to work out masses, so you can discuss that. So those are just from the last 3 years, and I think that's pretty much, okay, there's the hydrazine. Now I know I once made a wrong mistake. I hope that's the right one. I think that, sorry, I should have checked this. That may be wrong. I'll have to look it up. So, because I'm just trying to rush because it's after 4 now. Okay, Joe, This one doesn't have hydrogen bonding because the hydrogen is bonded actually to the carbon and not to the fluorine. So if you drew this molecule, carbon would be in the middle, 3 hydrogens attached to it, and 1 fluorine. So you've got 3 CH bonds and 1 CF bond, but no HF bond. So it can't form hydrogen bonds. Okay, so I want to sort of leave it there because I'm trying to keep these within an hour, because it's quite long for you to also sit and concentrate. If you've got any questions on today's lesson or anything like that, just send me an email and I'll do it in the next lesson. Otherwise, I'll go into entropy next week and a bit of thermochemistry. Okay, right, bye.